Okay, ladies and gentlemen, welcome back to our Manufacturing and Design MOW 217 lecture. So today we're going to do a quick review lecture of everything that we've covered this semester in MOW 217. So before I jump in, just to give you a brief overview again of the study themes that we covered. So we did Vesconite bearings, so there are a few calculation spreadsheets available over there as well. Semester test 1 also covered an example or a problem that you can use as an example to study these Vesconite bearing calculations. We then also looked at screws, fasteners, and the design of non-permanent joints. So this was mainly a theoretically based study theme over here. We didn't have any spreadsheets over here or design spreadsheets, but there are a few important points over here that we looked at regarding the actual construction of these screws and fasteners and some terminology associated with the threading as well. Then for study theme 4, roller bearings, our focus over there was mainly the design or the selection of these roller bearings, making use of the available catalogs that we also had. So we focused on deep groove ball bearings, as well as I believe your general roller bearings as well. So there is a quite an elaborate spreadsheet available for that. That then brought us to the gears and transmission systems, which also contains some theoretics regarding the setup of a gear, all of the properties of a gear, and then we also looked at how we can combine certain formulas based on the information that we have available to actually go and perform gear calculations and to find whether it is the base radius, the center distance between gears, or perhaps the pitch circle diameters as well. Right, so then for study theme 6, we went over to Fenner chain drives, which is then not one of our Shigley chapters that we looked at. Instead, in this case, we relied purely on the catalogs and the selection steps that we have available over there to actually design our chain drive mechanism and to then specify our drive with all of the properties that we need. Study theme 7 was then one of the last study themes that we looked at. Once again, mostly theoretical. In this case, we looked at the principles of mechanical engineering design. So the design process that you would follow if you wanted to create a new design, certain properties that we know are now iterative in the design process. And we said there's also some level of optimization that we want to achieve during this design process. All right, and then we also had a few guest lectures, but in addition to that, we also had a ninth study theme over here, and that regarded itself with some basic principles of additive manufacturing. So over there, we didn't look at any calculations, we just focused on the theoretical aspect. Okay, so to perhaps just run through all of these slides that we have available. So firstly, Vesconite plain bearings, we had quite a lot of information regarding this. So starting off with some theoretical properties and terminologies with regards to these bearings. The one that we were most interested in, or the part, or the section rather, was then with regards to the actual design of these Vesconite bearings. And this started over here on slide 18 of 44. So we had a few steps that we can actually follow over here for the calculation or the setup of our Vesconite bearings. So you can work through that as well for in preparation for the exam. Regarding the spreadsheet, we also had that available, so you should find that on ClickUp as well if you want to work through that. It also allows you to make any changes and to update your design properties using Excel and using a dynamic spreadsheet over there. Okay, so then moving over to Shigley chapter 8, which was then the screws and the fasteners. So once again, we had some background over here, some terminology that we had to take into account. Over here, you'll also see we have a few different properties of these fasteners that we take into account. So we basically discussed this across the slides. There are also, I think, a few standard equations or small formulas that we also imposed over here if you want to do some calculations. So over here, you'll see we simply use Newton's second law to actually determine the loading on a certain fastener on its thread and how that influences the actual operation of this fastener system. Okay, so then we have some more elaborate equations over here as well. If you, for example, want to consider the torque required um, in your system, then you can use these standard equations as well. So all of these are once again given in the lecture slides. These lecture slides will also be provided during the upcoming exams and the supplementary exam as well. So if you ever have to refer to the formulas, don't worry about knowing these things at the top of your head. We will make everything available for this. Okay, so to perhaps then jump over to the more elaborate design calculations that we did, we then moved over to the roller bearing system. So this was Shigley chapter 11. And over there, we also proposed a spreadsheet for the calculation of the different properties of the bearings. So we said if we have some sort of a bearing arrangement, we can use the information that is given, so the forces that are acting on these bearings, and we can actually go and calculate the radial load, the load factor, desired load and life, and we can use all of this to actually then formulate from our catalog what type of bearing we want. So if we're working with roller bearings, we have a set of tables for that in Shigley, and then we also consider the deep groove ball bearing, which had some interpolation and iterative design aspects over there. So in this case, we used table 11.2, and we could go and select the ball bearings based on the bore diameters and the load factors, all of these load calculations that we performed. All right, so this then brings us to the gears slides that we looked at. So this was Shigley chapter 13. So mostly we also had some terminology over here to look at. So if we have a certain gear, there are certain aspects that we need to consider, like the pitch circle diameter, where the addendum and dedendum circle sit, and they also influence the amount of clearance or the amount of backlash that I have, and then certain reduction methods that I can also use to either eliminate or reduce the backlash, which will ensure that my system is a bit stronger as well. So if we want to go down to, in this case, slide 19, this is where we introduced a few of the formulas that we will use for the design of these gears. And we can go and combine some of these formulas based on the information that we have available. So post semester test 2, we also looked at the contact ratio, which I believe is a bit further down. And over there, we actually considered how the contact ratio is then related to the arc of action and then the pitch circle as well. So we know that with regards to the gears as well, once we know what the geometry of the profile or the profile of the teeth look like, we could sort of formulate our base circles, and we know that regardless of the center distance between these gears, our base circle radii will always remain the same. It's a geometric or physical property of the gears. And we said with that, we can actually start building our problems or our design solutions further. Okay, so then we also looked at Fenner chain drive. So like I mentioned, this is not one of the Shigley chapters that we looked at. Instead, we actually relied on the selection steps and also the design data required, which is then given also in the Fenner chain drives catalogs that we have available. So we said that there are a bunch of selection steps that we can run through. All of the steps, or most of the steps actually, pertain to tables that we need to refer to in the catalogs that we have available. And in addition to these calculations that we perform, we might very well have some space constraints as well that we need to take into account. So this will influence the type of solution that we give. If we have perhaps fixed centers, or a case where our center distances is limited, then we might need to make a change regarding the optimal chain pitch that we choose, or we might have to use, instead of a simplex chain, we use a duplex or a triplex chain to make sure that our solution works. Right, so then we also said with regards to the chain length, we always want to make sure that we round up to an even whole number of pitches for our chain length. And once we've done that, if we don't have any space constraints, we can actually go and adjust the distance so that we ensure that we that we indeed get the rounded up value once we use the equation in step G. So step G is the step over here which gives us the chain length in terms of the other properties of the sprockets and of the actual chain itself as well. Right, so with that then done, the next study theme that we looked at was additive manufacturing, and this was a very broad overview of AM, so we didn't really go into any details with regards to calculations or how to set up STL files. Instead, we focused on what is additive manufacturing and the different types of additive manufacturing processes that are available. So we also compared the advantages and disadvantages of additive manufacturing with that of CNC. Over here, we did make reference to the fact that it is, in general, a bit easier to implement, especially as an end user. You might not necessarily have the knowledge of how to construct something using CNC or to manufacture something using CNC. However, 3D printing is then an alternative that you can use for that. It's fairly user-friendly, so that is also one of the reasons why we see additive manufacturing being used more commonly these days. So with regards to the additive manufacturing processes itself, we said there are different types of AM, so there are in total 7. We said material extrusion is probably the most common one that we are referring to always. It's the case where you actually have the material which is being deposited through some sort of a heated nozzle, and that material is initially supplied as a wire or a string or something that is then forced through this heated nozzle. A few other properties or types that we also looked at was then sheet lamination, binder jetting, material jetting, and then directed energy deposition, powder bed fusion, and then we have some light-based methods as well, like the VAT photopolymerization, okay, which actually uses UV light to cure the material once it's been deposited. Okay, so the material that we use for that is supplied in different manners. It can either be in a wire form. We can also have powder material and then also sheet material that we can use. And then, of course, for these VAT photopolymerization methods, we can use something like a resin over there as well. Okay, so that's just an overview really of the theoretical properties of additive manufacturing and its comparison with CNC. So once we were done with that, we then also moved over to Shigley Chapter 1. And this was then the principles of mechanical engineering design that we looked at over there. Short introduction with regards to what we expect from a mechanical design. We said it's a highly iterative process, so there's a lot of optimizations that are being performed, and an interactive process as well, in the sense that the design process that I follow, the processes or the steps in that process are interrelated. So whatever I get from one of the processes as output will then influence the inputs of the other processes. So speaking of the design processes, we also looked then at this schematic that we have over here. So we said we have in total 6 processes over here, but instead of simply running through them in a chronological manner, there's probably going to be some cases where I have to iterate. So for example, if I've performed my analysis and my optimization, then I can also go back to the concept design phase or the synthesis phase and go and iterate on those designs to make the analysis more reasonable if I want to rerun it. Okay, so then we also just looked at how to accommodate uncertainty in these mechanical engineering designs. So we said mathematical models aren't perfect in the fact that they don't really capture all of the experimental or the environmental conditions that we have. We do tend to make some assumptions that might not actually be valid in the physical realm. So instead, what we need to do is we need to account for any uncertainty in our models. So that is something that we looked at a bit further on, which I believe if I scroll down over here, you'll see over here we make reference to standards and codes, and this is one way to actually mitigate risks associated with the uncertainty that we have in our systems. If I go further down, you will see we also had, I think, some reference to the tolerances as well. So previously, when we looked at GD&T, we said we're not too interested in the actual value of the tolerance. Instead, for the purposes of MOW 217, we just want to use a reasonable tolerance. However, it is important to note that as the tolerances become finer, the cost of actually manufacturing this part tends to go up. And the reason for this is different tolerances require different machining operations. So we can see if we have some sort of a rough turn, our costs are still within a feasible range. However, once we want to start honing in on our manufacturing process, so the honing process, for example, which you have 6 micron tolerances over there, the cost has skyrocketed compared to your rough turn procedures that you have over here. So it's always important to take into account the tolerances that you use. And if you can rather use larger tolerances, then that would be more financially feasible. All right, so I believe the next thing that we also looked at then was the actual quantification of uncertainty. So in this case, we said we have deterministic and stochastic methods over there. So we can either use some sort of a factor of safety, or we can apply reliability methods over here, where we will then have reliability data or statistical data will then be required for the stochastic methods over there. Okay, so in addition to that, we also just ran through a quick example of dimensions and tolerances. So we said we can actually do a tolerance stack up if we're really interested in the reasonable tolerance values. So I'm just going to scroll down to this picture over here. I think it was over here. So we had an example 1.7 over here, where we then had some sort of a shouldered screw, and then we have 3 parts over here, and we can actually go and find the clearance and the minimum and maximum values based on our bilateral tolerances over here. Okay, so a fairly small example that that you should be able to do and understand. For the purposes of the GD&T or the mechanical drawings that we will provide you, you will not be tasked with performing tolerance stack-up analysis or any tolerance analysis. As long as your tolerances that you specify in your GD&T sketches are at least reasonable, then we're happy with that. All right, so I think this more or less then sums up the study themes that we looked at. So just a brief overview of all of that. So another thing that we looked at, which isn't really under the study themes over here, is then the GD&T, geometric dimensioning and tolerancing. Okay, so to illustrate that, I believe the previous review lecture that we did covered everything up to just before semester test 2. So perhaps it's a good idea for this activity to go through the semester test 2 memo and also the SIG test memo to explain what we are looking for when we're marking these GD&T problems. All right, so for semester test 2, we actually had 2 components. We had this pin rod end over here, and then on the next page you'll see is the bush rod end. So there's some interaction happening between these 2 components. You'll see that the pin rod end will basically slide into this bush rod end that I have over here. So some of the properties and some of the datum specifications also carried over between the two components over here. So let's perhaps first start off with the pin rod end that I have over here. So ideally what we first looked at is whether you defined your datum reference frame correctly. So whenever we have this type of system over here, you'll see we have a plane on this side, and then we also have a central axis running through here. And that is ideally how we want to define our datum reference frame when we have limited properties. So we can either define our datum reference frame where we have 3 orthogonal or perpendicular planes to one another. In this case, it wouldn't really be possible because we have a plane over here with another parallel plane sitting over here, or surface sitting here. And then we have a bunch of circular features. So instead of using 3 perpendicular planes, what I can also do is I can use one plane and then a central axis or a line to fully define my degrees of freedom. And this is exactly what we did over here. So if you had datum A and then datum B as your two datum features, then we mark that correctly or correct. Then it's just a matter of actually going and defining your theoretically exact dimensions. So bringing us to the theoretically exact dimensions, you'll notice we actually have a third datum over here called datum C. And we define this purely for the fact that we want to define the theoretical angle between these holes that we have over here on this pitch circle diameter. So I think there were quite a number of students that didn't include this datum C over here. If that is the case, an alternative that you can actually do is to say you have 3 times diameter 6.6 plus minus whatever your tolerance is, and then you just have to say equispaced on 45 PCD. So what you would do is the word equispaced would then be boxed, and your diameter 45 would also be boxed, but it's important that you then state equispaced. Okay, so in this case we don't actually need the datum C additionally because our section AA is through the middle. So it's and it's also going through these two holes that I have over here. So the diameter 6.6 clearance hole and this M6 by 1 hole that I have over here. So if I look at the section AA over here, I know that if they are equispaced, I should still have the diameter 6.6 hole sitting in the middle, and then the M6 by 1 hole, one of them sitting in the middle over here. And this is according to the section view over here. If I, for example, did not have the section view available, or my section view was at a different location, if I simply said equispaced, it means that these 3 holes could then rotate along this PCD and sit in any other place as long as the 3 holes are 120 degrees separated from one another. Okay, so this would then not be correct because I need one of those holes to be aligned with this vertical axis that I have over here. Okay, so then I can't simply use equispaced. Then I still have to say I'm going to choose one of these holes as a datum C, and then I have to give some sort of a theoretically exact dimension, and then if I want to, I can still say equispaced on whatever the PCD is. Okay, so additionally, with regards to datum C, you'll also notice that we use now 2 60 degrees over here, so 2 boxed 60-degree values. So the first one, if we look at that, is from this vertical line up to this first M6 by 1 hole that I have over here. And what we actually do over here is we extend this reference line over here all the way through so that it's in line with the one that's sitting opposite of this M6 by 1 hole, which is then this diameter 6.6 clearance hole over here. And then I simply add another 60 degrees over here, and I do it for this case as well. So if you were to not extend this line all the way through, then you would have to go and do 60 degree, 60 degree, and then add a bunch of additional 60 degrees as well. So instead, it's maybe just easier to extend this line that you have over here all the way through. Okay, so I think that more or less sums up then the theoretically exact dimensions that we looked at over here. A few other things that we then also noticed is that many students thought that instead of having 3 diameter 6.6 holes, that they thought all 6 of these holes were diameter 6.6, which is not correct. Reason being, if we look at these 3 holes that we have over here, so the M6 by 1 holes, you'll see there's a very small circle around this, around the nominal hole, or the nominal diameter that I have over here. So this actually indicates that I'm working with some sort of a metric size over here. So if I go and measure it, you'll see that the value that you get is then an M6 tapped hole that you have over here. So when we specify this, whenever we have a metric size, we always want to say M6 by whatever the pitch is. So you might have M6 by 1, M8 by 1.25, I think is also a standard value. So that's just with regards to the actual metrics of this tapped hole that you have over here. On the other hand, if you just have a hole with no thread around it, it's probably a clearance hole. So you'll see its diameter is 6.6. So this is also a type of a metric hole, but it's a clearance hole. So that's why it's a bit bigger than the M6 that we have over here. So yeah, so we just need to make a distinction between these two things when we actually define them in our GD&T. So in addition to that, because we have these holes, we also want to define positional tolerances. And since I have datum C on one of these diameter 6.6 holes over here, I just want to first denote this datum feature with respect to the existing datum features. So what I said over here is it should be positional tolerance diameter 0.2 with respect to B and D. And then if I now want to add for the other diameter 6.6 holes, then I can say there's two of them. And now their positional tolerances are constrained in terms of datums B, D, and C. So if you perhaps didn't have the datum C over here and you didn't have datum D, then you would have to do the equispaced on diameter 45 PCD specification. And then you could have said 3 times diameter 6.6 plus minus 0.2. Your positional tolerance would then be diameter, whatever you want this tolerance to be, with respect to A and B. So we also accepted that. Okay, so with that then being said, then we can actually go and focus on the actual rod diameters over here. So firstly, the diameter 20 that we have over here is going to interface with some sort of a bush or an interfacing component that's going to sit around it. So in other words, instead of using just a regular bilateral tolerance, what I'd instead maybe want to do is apply an ISO fit over there. So H7G6 is one of the standard ISO fits that we use. H7 referring to when you have the hole, and G6 if you have a shaft. And H7G6, I believe, is also a fit that a transition fit, I think is what we call it. Okay, so that's one of the standard fits that we use over there. So when you specify that, you just have to say diameter 20, G6, and then give the actual dimension over here. Then with regards to cylindricity and the surface roughness, these are also important since you're going to interface with some other component that's going to sit around it. So having a smoother surface finish is desirable, and then you also want to specify the cylindricity. Right, then we also just looked at the length that you had to specify for this feature. In this case, it was 80 millimeters. Then for the diameter 35, it's more or less the same as what we had for the diameter 20. So we still use the G6 fit over here. We once again have the surface roughness, we have the cylindricity specified as well. But now we have concentricity. So the reason for that is because firstly, we didn't have concentricity for diameter 20 because we specify its center axis as datum A, so that is the theoretically perfect central axis that we have over there. But now we need to make sure that this diameter 35 rather is aligned. Its axis is aligned with that of datum A's axis. Right, so that's why we then specify the concentricity, and we simply bind that with respect to axis A that I have over here. Okay, so once that is done, then I can also go and define the flange. So the flange is simply this surface over here. So we're going to have, perhaps if I can draw on this one, there will most likely sit some component over here on this side. So in other words, there's going to be interaction. So ideally what I want to do is perhaps define the surface roughness, or say surface roughness 1.6 for that. And then I also want to make sure that it is concentrically bound. In this case, we specified that as D. Alternatively, you could have also said concentricity diameter 0.4 with respect to A. That would have also been fine if you don't have the datum D available. Okay, so yeah, and then you just have to give the size over here as well. In this case, we don't give it as an ISO fit because this is actually going to sit on the outside. So it's not going to have any um, component into which this flange is going to fit. So instead, since it sits on the outside, we can just use a normal equal bilateral tolerance for that. Okay, and then we also just looked at the overall length, whether you specify that. And in this case, you'll see it's once again a reference dimension. So the reason for that is I actually have enough information to define this 128 from my individual dimensions. So I have the 80 millimeters over here. I have a 40 millimeters over here. And then I also specified this 8 millimeter flange over here. So if I add all of them up, 8 plus 40 plus 80, I will get 128. So instead of giving this as a tolerance dimension, I'm just going to give it as a reference dimension so that the manufacturer is aware of what the overall length should be. So when they use this for packaging purposes, they can just refer to this value over here. Okay, so that more or less then sums up the pin rod end. So the bush rod end you will see is now more or less the same. In this case, I then have datum A, which is then on this diameter 35 that I specified over here. So once again, I make use of an axis and a plane to fully define my degrees of freedom so that if I have any of these holes and I want to lock them in positionally, then I have enough information available to do that, or enough datums to do that. Okay, so similarly, we also defined datum C over here on one of these diameter 7 holes. So that's once again a clearance hole. And then we also have these 3 holes which are M6 by 1. And we can see that they are threaded. So because of that, whenever we give the size or the depth of these holes, we can see that there's a thread depth. And then we also have the overall depth. So I need to specify both of them when I define this M6 by 1 hole. So other than that, the positional tolerances and everything remain the same. Remember that if you didn't have, in this case, datum C, because my section BB actually sits through the diameter 7 and the M6 by 1 holes, I can simply say equispaced on diameter 45 PCD. Remembering to place equispaced in a box because it's theoretically exact. And then I also want to place this diameter 45 in a box as well. Okay, so then just something that I also want to point out is with regards to detailed drawings. So if you perhaps feel in the exam or any upcoming assessments that you do not have enough enough space to really show what's going on over here, you can always just draw a circle around it and refer to it as a detailed drawing. So just draw it a bit bigger on your drawing or on your page over here, and then you can start dimensioning that accordingly as well. Okay, so I think this more or less then sums up what we did for semester test 2. So next up, I just want to jump over to the SIG test example as well. And you'll see this is more or less the same as what the semester test was. We also have a bunch of circular features over here. In this case, the students were just tasked with actually drawing the system on their own. So we can actually ask you to draw it, but we won't make it too difficult if you have to draw it. It will be a fairly simple design that you will just have to redraw and then GD&T that design. Okay, so looking at the properties over here, so we have a Vesconite bearing that we need to tolerance. So perhaps once again, starting with the datum reference frame. In this case, you'll see there's only a datum A. I think some students might have wanted to add a datum B as well. So that would be fine if you added the datum B, let's say, as perhaps this surface over here. So if I maybe go over here and I draw it. Right, so we could perhaps, let me just reselect this. Then we could perhaps draw it up over here and we could call this datum B. Okay, so that would also still be fine. My suggestion would then be if you define this as datum B, that you then just constrain it perhaps perpendicular to whatever datum A is. So that makes so that you have sort of a connection between your different datums in this case. All right, so and then I also just want to do exactly the same on the other side of this flange over here. And this is mainly because I'm going to have some interfacing component that's going to sit on this side. So constraining it perpendicular with respect to A is also desirable over there. Okay, so in addition to that, we didn't have any holes that we had to specify for positional tolerances. Instead, we want to focus on the fact that these circular features need to be concentric with one another, so coaxial, so their axes need to lie along the same line over here. Okay, so perhaps just first starting off with our inner diameter over here. We have diameter 40.56 plus minus 0.025. You could have perhaps used, I think, an ISO fit as well, so an H7 fit if you wanted to, but if for the purposes of this study, just using a bilateral tolerance would also have been fine. Once again, it's going to interface with some component or shaft that's going to sit over here. So in other words, I'd like to specify the cylindricity and then also the surface roughness to be a bit smoother. So just important to note, if you don't specify the surface roughness, the standard surface roughness is usually 3.2. So it's a bit more coarse than what you would have for the 1.6 surface roughness. Okay, so once that is done, I can then go over and dimension the diameter that I have over here. So in this case, it's a reference dimension. It's simply given for information, and this might be because it's a standard size. So we use diameter 60.2, but we can still go and apply a concentricity to this specification. So we can still say it should be concentric, diameter 0.05 with respect to A. So A is the central axis of the inner diameter. And now we're just saying we want the central axis of the outside diameter to also be coaxial or collinear with the central axis for A. Right, so in addition to that, we can then also go and I think define just your overall lengths. So in this case, you'll see we have the flange thickness that we specify, so 9 plus minus some sort of a tolerance. And then we also gave 49 plus minus 0.2. In this case, it's not a reference dimension, mainly because I didn't specify what the size over here is. So if I say from here up to here, so I didn't specify this size over here. Okay, so I don't have to give it as a reference dimension. If I did specify, let's say 9 plus minus 0.2, and over here I said 40 plus minus, let's say 0.1 for example, then this 49 would have changed to a reference dimension, because then it's a combination of dimensions that have already been given. Okay, and then lastly, I just want to point out as well that you also need to go and define your chamfer dimensions. So this is what we did over here. Typically, when we specify a chamfer dimension, we give a linear size, and then we also give an angular size. So in this case, you'll see it's 15 plus minus 0.2 by 30 degrees plus minus a 5-degree tolerance over here. So similar for millimeter tolerances, for these degree tolerances, we also don't have a set value for that. If you, for example, wanted to use something like plus minus 1 degree over there, we would also accept it. So the reason why we specify a chamfer like this is, if I perhaps go back and I draw it again. So if I have my chamfer like this, if I give this size over here, so in other words a linear size, and I also give the angle over here, then I have enough information to fully define the chamfer. Okay, so it's good practice to always give a linear dimension plus the angular dimension. Right, so I think that more or less then sums up the GD&T aspect. So finally, it's just a few comments that I also want to make with regards to the conceptual designs. I've had a few queries with regards to how to go about conceptual designs. So you've had now with semester test 1, 2, and also for the SIG test, some experience with developing a concept. So the idea over there is that when we give you the problem, it's a good idea to first go and define the problem in your own words, understand what the user requirements are as well. So you'll remember for semester test 2, you were tasked with creating an auto slider, basically, using a rack and pinion system. So one of the user requirements would be that a rack and pinion system is required. So my suggestion with those type of questions would be to always start off by considering what you need to use, and then the next question would be how to actually use it. So look at where I can apply it, what are any of the interacting components that I also need to take into account. So for example, we had a motor that you had to also place in for that gear rack and pinion, or that rack and pinion design for the concept in semester test 2. So you're probably going to have some motor and a motor mount, and then because there's a shaft interface as well, you'd probably want to add some bearings as well to ensure minimal vibration effects during operation. So rather look at the broader aspect of the concept as well, and always start with the user requirements first before you move forward. Okay, so moving on, I just quickly want to give you a breakdown of what we expect for the exam scope, or the exam breakdown as well. So the first section will be theory and calculations, or let's rather say there will be a section on theory and calculations, so that will count 40% toward the exam. So short questions, so these are the auto-graded type questions. You've now had experience with that during semester tests as well. The AMS auto-graded questions, where we have some sort of a design that we want you to calculate. So that will count approximately 30%. There might also be a few theory questions in between that we want to evaluate you on, so true or false questions or any discussion questions as well. And then there will also be a long calculation question, so one where we will manually grade the actual values that you get out, the formulas that you used, and whether you are knowledgeable in actually setting up the formulas that you need to use. Right, so then the second section, or the next part that we will also evaluate, will then be the GD&T, and this will also count then 40%. So this will be a question or two where you have to go and apply GD&T to some mechanical drawing that we give you. So we'll provide you with any step files that you also need to use. So make sure that you are by now familiar with the fact that you have to use FreeCAD and the manipulator workbench to go about getting any measurements, and make sure that you are also on par with all of the GD&T that you can apply. And then finally, we will also ask you a conceptual design question. So this is the last 20%. So that is what we just discussed as well, a similar type of question like that. So in that case, just also remember that these conceptual design questions are considered the distinction question. So they are made to be difficult. And if you are really adept with solving these type of conceptual design problems, then you'll do good. But overall, we reserve this type of question for the distinction students, or the students who are quite familiar with conceptual design.